You hold on to it for me. We're looking at number 3 from 2.1's homework. It says find the slope of the tangent line to the parabola, and we're given the function y equals, what was that again?
4x minus x squared.
And it's at the point.
1.
All right, so if we're looking for the slope of the tangent line, me personally, well, you can use either formula, but me personally, I tend to lean on this one. The limit the limit as h equal to 0 of so we want to use the limit as x approaches a of f of x minus f of a over x minus a. And in this case, my a is positive 1. So we know y is 4x minus x squared. We know y is also f of x, or another way of writing y is f of x. So this is my f of x, 4x minus x squared. So when we're evaluating this limit, we're actually evaluating the limit as x approaches 1, because a is 1, of f of x, which is 4x minus x squared, minus f of a, keeping in mind that a is equal to 1, this would just be 4 times 1 minus 1 raised to the second power. And it's all been divided by x minus 1.
Okay. So I got confused.
Mm-hmm.
Because I thought f of a was 3.
You said f of a was 3?
I thought. That's why I got confused.
Well, I guess technically that would be true because you're talking about the order pair 1, 3, because if x is 1, then y is 3. So, and we can work that out and see, but I'm assuming that you're right too. Let's see, the limit as x approaches 1, 4x minus x squared minus 4 times 1, obviously is going to give me 4. Minus 1, yeah, that is just going to be 3 over x minus 1. So, still evaluating the limit as x approaches 1 for 4x minus x squared minus 3 over x minus 1. We can rearrange that. That as x approaches 1. For me, I'll probably rearrange it as negative x squared plus 4x minus 3 over x minus 1. Factor out that negative 1 up top just to make it match form and see if we can factor. I don't believe this is factorable. I may go back and look at this one, but that'll be minus. Sorry. All right, so all I did up top was factor out the negative 1 because the quadratic we were given with negative x squared plus 4x minus 3. To get it to match form, we can factor out negative 1. This way, that x squared is positive. And now we can factor that x squared minus 4x plus 3, looking for 2 factors of 3 that we can combine to get negative 4. Obviously, that's going to be 1 and 3 because those are the only factors of 3. So we're still evaluating the limit as x approaches 1. Factor out that negative 1 to completely factor the form of the quadratic x squared minus 4x plus 3 will be x minus 1 and x minus 3. Here, my x minus 1s will cancel. And the reason that's important is that now we're going to be evaluating the limit of a polynomial. The reason that's important is we can solve all polynomial problems through direct substitution. Now we're evaluating the limit as x approaches 1 for basically negative x plus 3. All we did, distribute that negative 1 and multiply the only factors we had left. And now we can solve the direct substitution. So we'll end up with negative x plus 3 or negative 1 plus 3, which ends up being 2. So the slope of the tangent line here will be 2 using the definition. Now I can tell you now what 2.3 Once you learn those formulas, and if you're a person that understands the general power rule, then you're going to know right off the bat that this is a whole lot of tedious work, but you have to show that you're able to do it. This is why I ask on the test probably 2 problems like this. All right, any questions on this though? Yes, sir. Go ahead.
Is that, did you just replace the -1 3 with the 2 formula figure, or where did that
Hold on, say that one more time. I want to make sure I understand your question.
come? The x,
Right here.
the x squared minus 4x plus 3, right?
Mhm.
And you factor it to be x minus 1.
And that x minus 1 times x minus 3, exactly right. Now, before I factored it, though, I had to get rid of that negative coefficient in front of x squared. That's why I put it at -1. Now I can factor it like a trinomial I typically use to factor it. So, say that again. All right, but remember also with the calculus, it's the algebra that throws you off. This is a part of that algebra. It's like 7 different common factoring techniques that people know at the back of their head. Now, that's not the only ones, but you have to be real versed in fact. So I can tell you right now, trinomials with a leading coefficient of 1, that's these type, the ones you're typically used to saying. And trinomials with a leading coefficient of something other than 1, like I think it was like a 2t squared plus 7t plus 3, like on a test that you had at the bottom of the problem, something like that. You got to know how to factor these type. Well, my suggestion is you need to know how to factor these type and these type in your sleep, because you're going to see a lot of them in these type of problems. All right. Any other question though? Yes, sir.
Oh, those laws or something. Is that something like that? Are we allowed to have it on the cheat sheet for the test?
Oh yeah. Any laws, any definitions and stuff like that, that'll work. Biggest thing, no work problems. Like if you had a limit law problem, that's what I'm thinking you're asking me about, and it was really, really difficult. So you thought maybe I'll just write this one on the cheat sheet, bring it in. If you bring that in, I gotta take it from you. But any of the definitions, the laws themselves, yeah, that's fine.
Okay, so that is my question that I asked earlier. I remember you gave the definition of the tangent line to the curve y equals f of x to the same point p a.
All right, so 2.2. Right off the bat, looking at derivative as a function and how it relates to the slope of the tangent line and its applications. So in 2.1, in the preceding section, we considered the derivative of a function f at a fixed number a, 1. F prime of a is equal to the limit as h equal to 0 of f of a plus h minus f of a all over h. Keeping in mind, this is just one of the 2 slope of the tangent line or derivative formulas that we have. We could also use x approaches a to give us the same answer. In 2.2, here we are changing our point of view, and we're going to let the number a vary. So if we replace a in the equation 1 with the variable x, then we obtain f prime of x, which is equal to the limit as h approaches 0 for f of x plus h minus f of x all over h. So as we're copying this down for the ones who are choosing to do so, this is simply saying that we're now taking it from looking at a specific value on the x-axis, and we're going to allow a to vary to where we can get an expression that represents the slope of the tangent line, or in this case, our derivative, despite what x is equal to. Once we get that expression, all we have to do is simply look at what x is, and it can vary, plug it in, work it out, and we have the slope of the tangent line at any given point. All right. All right. So what we're going to remember is that here we're talking about the derivative, but don't forget that the slope of the tangent line, or the slope of the line tangent at any point x, is also the derivative. So all of this still holds true for the slope of the tangent line as well. All right, so in example 1, we're going to be looking at a graph. And if you follow along in the text, we're looking at the graph, figure 2 at the bottom of page 118. It says the graph of the function f is given in figure 1. Use it to sketch the graph of this derivative f prime. All right. So here's a general sketch of our graph. I'm drawing it freehand. And you see that arbitrary function, y equals f of x. We really only signify one particular point on this graph P, which is the ordered pair. Oh, excuse me, that point P, at that point, the slope is roughly 3/2. All right, so we're going to use the characteristics of the graphs when it comes to the graph of the original function f and the sketch of the graph of its derivative, f prime. We're going to use the fact that the derivative is the slope of the tangent line. So technically, when we have the slope of the tangent line, and we have when we have an arbitrary function or an expression representative of the slope of the tangent line at any point, we can use that fact to get us some characteristics on the sketch of this derivative, as well as some characteristics between the function f and f prime. So like I said, we can see we have arbitrary function f of x coming in, and then went out of his way to make note that the slope of the tangent line at this point, roughly 3/2. All right, so if we remember, when it comes to the slope of the tangent line, we know all horizontal lines or horizontal tangents have a slope is equal to 0. This is because all horizontal lines slope is equal to 0. All right, so remember, perfect horizontal line left to right, slope is equal to 0, which means that the slope at that given point is the slope at this given point maps to the x-intercepts on the graph of its derivative. So looking at the sketch of this function, we can see that we do have horizontal tangents. Remember, a tangent by definition is where it intersects the graph in exactly one spot. Here, where it turns from decreasing to increasing, that turn gives us a horizontal tangent right here that's perfectly horizontal, where my slope is equal to 0. Where it goes from increasing to decreasing again here, another horizontal tangent. Where it goes from decreasing to increasing here, around 3, another horizontal tangent. Whenever we find horizontal tangents, that means the slope is equal to 0. The slope of the slope at a given point is the y value on the sketch of this derivative. So remember, this is the sketch of our original function f. This is the sketch of our derivative, f prime. Now, as far as those x values go from the sketch of the function and its derivative, they basically are mirror images of themselves. So this horizontal tangent obviously happens somewhere in between 0 and 1. Now, because we're given the sketch, we don't have to be exact, but it should be in between 0 and 1. Because this slope, or the slope of the tangent line at this point, is equal to 0, that means the y value, or the x-intercept on the sketch of its derivative, is equal to 0. If y is equal to 0, it intersects the x-axis at that point. All right, so if this, on our original graph, we'll call this point A, where we have a horizontal tangent, then this is A prime, or the derivative at that point. So here, we have another horizontal tangent in between 1 and 2, which have another x-intercept right here in between 1 and 2. If this point is called B, then this would be B prime. And we have another horizontal tangent that occurs right here. We'll call this C, right at 3 on the x-axis. This maps to an x-intercept at 3 on the sketch of its derivative, or f prime. And we'll call this point C prime. So here, I'm going to introduce some y values, call that 1 and 2 here. So at this point P, where the slope is roughly 3/2, remember, the sketch of the derivative holds true for any x value. Horizontal tangents is basically low-hanging fruit that maps to x-intercepts, and we can get them relatively easily, so why not go ahead and grab those? All right. Now, this point P, this shows that it really is that we could do this at any point on this graph. The slope of the tangent line is the y value on the graph of this derivative. So this slope at point P, the slope of the tangent line is roughly 3/2 or 1.5. So at 5, we're going to go to 5 on the x-axis on the sketch of this derivative and go up 1.5 units. So if this is 1, this is 2 on the x-axis, 1.5 would be right here. And this would be my point P prime at the ordered pair 5, 1.5. All right. So that's our first, or the first characteristic that we're looking for the sketch of the original function f, and how it maps to the graph of its derivative f prime. Horizontal tangents map to x-intercepts. But this is true because the slope at any point x of the tangent line is the y value for that exact same x on the sketch of its graph on the graph of its derivative, should I say. All right, the second thing, or second characteristic is going to help us sketch this graph is the fact that if on the original function, f, on that interval, if it's decreasing, for example, like from here, it's decreasing from negative infinity all the way up to 8. On the original function, f, if the interval is decreasing, that means that it's below the x-axis on the derivative, on the sketch of the derivative. I'm gonna say it again. Don't get me wrong. It felt confusing coming out my mouth. So one more time. On the original function, f, if we're looking and tracing the function from left to right, if f is decreasing on the interval, like from here, it's decreasing from negative infinity all the way up to 8. This means that those tangent lines, their slopes are negative until we turn here where those tangent lines turn to where they're positive, the slope of those tangent lines, should I say. So if it's decreasing on the sketch of the original function, that means that it's below the x-axis on the sketch of its derivative because negative values are below the x-axis. And remember, the slope of the tangent line is the y values on the graph of its derivative. So here, from negative infinity to a, this interval is decreasing from left to right, which means from negative infinity to a is below the x-axis where the negative values would lie. Now, between A and B, is that interval increasing or decreasing? Increasing, which means the slope of the tangent lines on this interval are all positive. If they're all positive, they should be above the x-axis because these y values that are positive are above the x-axis. So in between A and B, that interval is increasing. So in between A prime and B prime on the sketch of this derivative, it should be above the x-axis. Say that again. No, not necessarily 1.5 because 1.5 is associated with the point P, and we're not at P prime. All right, so remember, we're talking about all those arbitrary tangent lines and the slope of those tangent lines in between a given interval, which is a mouthful to say, but at the end of the day, if it's increasing on the sketch of the original, above the x-axis on the sketch of its derivative. It does, but remember, we're just giving a quick sketch of it. We're looking for what to expect on the graph. All right. And between B and C on the graph of the original F, increasing or decreasing. So in between B prime and C prime, should we be above or below the x-axis? Below. So in between B prime and C prime, we need to be below the x-axis. And then from C all the way to infinity, going through that point P, is this increasing or decreasing? Increasing. So from C prime going through P prime all the way out into infinity, we should be above the x-axis. So biggest thing is that we're above the x-axis and we make sure that we're going through P prime and it continues to increase all the way out through that interval. This says that all the slopes of the tangent lines for this interval are positive. And if we introduce a slope, let's say here, that tangent line right there where it intersects exactly at one point, the slope of that line would be positive or negative. Hold on. Would it be positive or negative? All right, so at this arbitrary point in between C and P on the graph of the original, we introduce a tangent line where it intersects the graph exactly one spot. Is this line, the slope of this line, positive or negative? Positive. Because if you're looking at it from right to left, moving up the page, slope is positive. And this is true for every single point in between C and P, which means that every single point in between C prime and P prime has to be above the x-axis, because that's where all the positive y values, which is the slope of the tangent line for the original function, lies. All right, any questions on this? Keep in mind, we had a lab about this. The lab is what's going to really help you as long compiled with these examples of things that we already know. Here, this is an arbitrary function, so we don't really know where this shape came from. When we start using some examples, we're going to use some functions that we're used to and their derivatives, something that we can easily prove through some algebra and show that these characteristics that I'm telling you, I didn't just pull out of the air. All right, they hold true in every single case. That's all.
So is there a tangent line for C prime, or is there?
For C, well,
Is there a tangent line for C prime, or is it just not?
we're not worried about C prime because C prime is a derivative, and that's what that maps the slope of the tangent lines.
Oh, okay.
So there is a tangent line for C, and that tangent line is perfectly horizontal. That's why C prime is the next intersection. Well, no, everything matters. So what do you mean by it?
I'm just saying if there was a tangent line for C prime, because I want to say there's a direct correlation between C and C prime.
Yes, there's a relationship between the two, but yeah, when it comes to a tangent line on the graph of the derivative, we're not worried about that until we get into higher order derivatives, which we will do, but that's a different problem for a different day. All right. Any questions on example 1 though? All right, put a star beside example 1. These characteristics are what we're going to be looking for our lab on Friday. So even if these characteristics didn't make sense, put a star beside it because our lab, and we start to get confused, we can refer back to this example. All right, example 2 is a first opportunity for us to show that these characteristics hold true with something that we're used to. And by something, I mean functions that we're used to dealing with. So in example 2, it says if f of x is equal to x cubed minus x, find a formula for f prime of x. And part B, illustrate by comparing the graphs of f and f prime. All right, so the first part of example 2, we're given f of x is x cubed minus x, and we're asked to find the formula for f prime of x, which is good because we have a formula for that. So working with the given function, f of x, which is x cubed minus x. All right, so given that f of x is x cubed minus x, for part A, the formula for f prime of x, remember we can use either of those two limit definitions for the derivative. I personally lean towards the limit as h approaches 0. So we're going to have the limit as h approaches 0 is equal to f of x plus h minus f of x, and this is all being divided by h. So in this case, this will be the limit as h approaches 0 for x plus h quantity cubed minus x plus h minus x cubed minus x, and it's all being divided by h. All right. Now, typically is we have some people who have a question at this point, but they know they should know what they don't know. Are there any questions at this point that I need to go over? Well, no, we don't have to use the limit laws here because we can simplify using some algebra. But if we tried to use the limit laws, it wouldn't work because on the bottom we have the limit of h is h equals 0, can't divide by 0. All right. Does everybody understand how we got the expression x plus h cubed minus x plus h? All right. Appreciate the honesty. So remember, when we're evaluating something, let's say if we're given f of x, which is x cubed minus x, and we're asked to evaluate f of 1, what will we do? Plug in 1 at where at? All right, so we plug 1 in for every x in f of x, which is a mouthful to say, not a whole lot to do. This one would be 1 cubed minus 1, right? So if we're evaluating f of x plus h, the rules for functions have not changed. We're still essentially substituting. We're going to replace every x in f of x with x plus h. So f of x, which is x cubed minus x, becomes x plus h cubed minus x plus h because we have substituted x plus h in for every x in f of x, which is a lot to say, but it's not a lot to look at. So this makes sense, right?
No.
I know because you was listening to me. Look at what I'm doing.
Okay.
All right. But you said you understood it before the question was asked. So don't allow me talking to confuse you. Know what you know. But for the ones who didn't understand it before I started talking really, really quickly, does it make sense now? Be honest with me. I'll say it again, I'll slow down too. All right, so with a function f of x is a rule that we follow. If we're asked to evaluate f of some value, all we're doing is essentially substituting 1 in for every x we see in f of x, which is a lot to say, but that just means we're here and here, we're gonna plug 1s, right? That's what we did. So when I'm asking in this limit definition to evaluate f of x plus h, which is a lot to say, makes me sound smart, but it's not a whole lot to look at, right? All we're doing is substituting x plus h in for every x in f of x, which is confusing to the ear, but essentially here and here, we're plotting x plus h. This is f of x plus h, which is x plus h cubed minus x plus h. At the end of the day, we're still substituting. All right, it really sounds confusing to the ear, but if you look at what I'm saying, it makes sense. Hopefully. This is where y'all tell me something.
That you was plugging in that problem inside the formula. I guess my algebra was off about the x plus h cubed and the x plus h. You know what I mean?
Well, we haven't started working it yet, so that maybe that's what the issue may be, is that you already taken the next step.
Yeah, I see where you put in the really plugged in form, the x minus 3 and the x to replace the regular x. That,
X plus H, but yeah, go ahead.
I get.
Okay.
I guess I just got lost with how to get the setup.
All right. I'm gonna keep on going. Hopefully that makes more sense, okay? Now what we need to do is simplify this down. Now x plus h cubed, by definition, that's x plus h times x plus h times x plus h. Now we can FOIL that out and then distribute x plus h again, but I have no doubt we can multiply that if we needed to, or we could bring in a formula for x plus h cubed on a formula sheet so we can cut down on some time, and I wouldn't have any problem with that. All right, so just remember that x plus h cubed is equal to what I'm about to write. Probably a good idea to write it down and put it on your formula sheet, okay? So x plus h cubed gives me the expression x cubed plus 3x squared h plus 3xh squared plus h cubed. Every single time, it'll never change. X plus h cubed, or x plus h times x plus h times x plus h, gives me the polynomial x cubed plus 3x squared h plus 3xh squared plus h cubed. All right, continuing to work. We need to distribute this -1 here. So that's going to be a minus x minus h. We also have an understood -1 here. So that's going to be minus x cubed plus x. This entire polynomial still being divided by h. Now we're going to go through and see if we have any like terms that we can combine. If we're doing this correctly, everything in f of a will cancel out every single time. So for me, I like to start from the right, working left. We have a positive x, we have a negative x. Those are going to cancel. We have a positive x cubed. Oh, excuse me, we have a positive x cubed. We have a negative x cubed. Those are also going to cancel. If we're doing this correctly, every single time, every term that we have left over in our numerator will have at least one h in common. So here we have the limit as h approaches 0 to 3x squared h plus 3xh squared plus h cubed, and this is all being divided by h. Notice how everything in our numerator has at least one h in common, because one thing that happens every single time. Oh, but that's another age, though. I appreciate y'all. I've been looking for a living. All right, but still, every single term in my numerator has at least one h in common. So we can factor out an h. Now we're evaluating the limit as h approaches 0 for h times 3x squared plus 3xh. You know what, I'm gonna bring this down here. But we have h times 3x squared plus 3xh plus h squared minus 1. And this is all still being divided by h. Those h's cancel, and that's important, but that's because it takes it from a rational function to a polynomial function, which means that we can solve it through direct substitution. A lot to say, a lot to understand, very little to do. All right. So now, everywhere we see h is just going to essentially be 0. So 3 times x times 0, that's 0. 0 squared, that's 0. Our answer, or the expression that represents f prime of x, the slope of the tangent line at a given x, would be 3x squared minus 1. This is a reminder because it's easy to get lost in the sauce. F of x, x cubed minus x. These are the two graphs that we're going to be comparing, looking for those characteristics. And by those characteristics, I mean horizontal tangents and how they map to x-intercepts, increasing and decreasing intervals and how they map to y values being above and below the x-axis. All right, so now for part B, what we're going to do is compare the graphs of f and f prime to see if those characteristics still hold true from example 1. All right. So the graphs that we're going to compare here, example 2, part B, we have the graph of f, which looks like so. So that's the original graph of f of x, or x cubed minus x. All right. And then we have the graph of our derivative, which we found to be 3x squared minus 1. All right. So the sketch of that graph. So very ugly parabolas. But the sketch of that graph look like so. That's gonna bother me. Let me draw it again. All right, and this is the sketch of f prime, or the derivative of the given function, which we know to be 3x squared minus 1. Notice that those characteristics still hold true. And the original function, we have an increasing, then a decreasing. This maps to a horizontal tangent here. Horizontal tangents on the original function map to x-intercepts on the graph of the derivative. Notice that we have an x-intercept in between -1 and 0 on the graph of the derivative. We have a horizontal tangent in between -1 and 0 on the graph of the original function. That's not by coincidence. Same thing here. We have another horizontal tangent below the x-axis on the graph of the original function f in between 0 and 1. Notice how that maps to an x-intercept in between 0 and 1 on the graph of this derivative. Our first interval is from -infinity all the way up to that first horizontal tangent, or from -infinity all the way up to my x-intercept on the graph of my derivative should be above the x-axis. This is because this is an increasing interval. Therefore, the slopes are positive. In between my first horizontal tangent and my second horizontal tangent is the only interval of decrease I have on the graph of the original function. Notice how in between the x-intercepts on the graph of the derivative, this is the only interval that's below the x-axis. This is because the slope of the tangent lines in this interval are all negative. Therefore, all the y values should be below the x-axis. Lastly, from the horizontal tangent all the way out to infinity, this is an interval of increase, which means it should map to an interval that's above the x-axis on the sketch of the derivative. From the x-intercept all the way out to infinity, notice that this interval is above the x-axis. This is because the slope of the tangent lines on that interval are all positive. Therefore, the y values on the graph of the derivative should be all above the x-axis. All right. Any questions on the comparison of those graphs in example 2 in particular? Or any questions on example 2 at all? All right. So really, if you're looking at the original function, if it's increasing, that's above the x-axis on the graph of the derivative. Decreasing, that's below the x-axis on the graph of the derivative. Increasing, that's above the x-axis on the graph of the derivative. So we went from, we should have above, below, above. When we look at the graph of the derivative, we're above, below, and then above. All right, so that characteristic holds true. The interval of increase on the graph of the original function should be above the x-axis, that interval, should I say, on the graph of the derivative. If it's negative, the interval of decrease, should I say, on the original function, that interval should be below the x-axis on the graph of the derivative. Horizontal tangents are my x-intercepts. Where they occur on the graph of the original function is where they occur on the graph of the derivative. All right. Now remember, this is a lot to say. It's not a whole lot to look at, but you got to kind of get used to how it relates to itself. Like I'm going increase, decrease, above and below. More than likely, when I say increase, decrease on one, you want to think increase, decrease on the other. And that's not the relationship. Same thing with horizontal tangents. Okay, horizontal tangent here, your intuition wants to tell you horizontal tangent here. But horizontal tangents relate to x-intercept. So horizontal tangent, x-intercept. Increasing above the x-axis, decreasing below the x-axis. That's what we're looking for. Okay? Yes, ma'am.
I mean, although this is a positive dilemma, we're not really.
Go ahead.
Do I say limit?
I'm not sure. Ask your question.
Okay. So although like it's going up, but it looks as if it's going down.
When you say it, are we referring to the graph of the original? Okay, so the derivative?
Yes,
All right.
although it's a positive, it's going positive spin.
Oh, you mean like, is this reaching towards positive infinity? Yes. Now that doesn't relate to the relationship between the original function and its derivative, but that is true. Okay. All right. But do you see the relationship of what we should be looking for? Like, even if this doesn't make sense right now, you got it on video, you can go back to it, you can back the rest of your life to make sense out of it. The thing that you got to remember is that horizontal tangents, x-intercept. That's from the original to the derivative. Increasing above the x-axis, decreasing below the x-axis. That's from the original to the derivative. So here, horizontal tangent. Horizontal tangent mapped to what? Brave soul. X-intercepts. You're right, x-intercepts. Horizontal tangent means that where this occurs is going to become an x-intercept. Notice that we have a horizontal tangent in between -1 and 0 on the graph of the original function. Where's my x-intercept located? -1 and 0. That's not by coincidence. It's going to happen every single time. As a matter of fact, it happens again right here. We have a horizontal tangent in between 0 and 1. Horizontal tangent maps to what again on the derivative? X-intercepts. So we should have an x-intercept in between 0 and 1. Don't we have one? All right, so increasing, decreasing. Remember, if it's increasing on the graph of the original, what should happen on the graph of the derivative? It should be above the x-axis for that interval. This interval is from -infinity all the way up to my first horizontal tangent, or on the graph of the derivative, from -infinity all the way up to my first x-intercept, because that maps to my horizontal tangent. It should be above the x-axis, and that's exactly what it is. In between my first horizontal tangent and my second horizontal tangent is an interval of decrease. That means that on the graph of the derivative, it should be below the x-axis for that interval. In between the x-intercepts, because horizontal tangents map to x-intercepts on the graph of the derivative. You see how it makes me sound smart? Like I got a lot of words to say, but we're not really looking for very much. All right, so for this interval, we should be above or below the x-axis. I'm asking. Below. In between the x-intercepts, we're below. Okay, let's move to another example because I feel like another example will help. So you can kind of see how these things relate despite the function. All right, so in example 3, it says f of x is equal to the square root of x. Find the derivative of f and state the domain of f prime. All right, so we're given f of x is equal to the square root of x. We're asked to find the derivative. We have a formula for it. So we're going to start with the limit as h equals to 0 for f of x plus h minus f of x all over h. Notice that every single time I'm doing this problem, I write out the formula. The more you write it, the more likely it is for you to remember. All right, keep in mind, the way I look at it, if you write it every single time you have the opportunity, it's not that you have to remember it, you can't forget it. Now here in this problem, we'll be evaluating the limit as h approaches 0 for the square root of x plus h minus the square root of x all over h. All right, so it sounds like we recognize we're going to have to use a conjugate here. If we have a summation or a difference with radicals up top, and we have arbitrary values, x's, it could be perfect squares, it could not. If x is 9, that works. If x is 10, it doesn't. So it helps for us to rationalize the numerator, and the way that we're going to do that is using the conjugate. And the conjugate for the square root of x plus h minus the square root of x would be the square root of x plus h plus the square root of x. So we're going to multiply both the top and the bottom by the square root of x plus h plus the square root of x. So up top, we're going to have to FOIL this out. The square root of x plus h minus the square root of x times the square root of x plus h plus the square root of x. We have the square root of x plus h times the square root of x plus h. This is going to give me x plus h. We have the square root of x plus h times the square root of x, a positive square root of x. That's going to give me the square root of x times the square root of x plus h, a positive value. Notice that where I'm not writing it down, because by nature of the conjugate, the outside terms and the inside terms are always going to cancel. So we have a positive square root of x times the square root of x plus h. My inside terms, a negative square root of x times the square root of x plus h, will give me a negative square root of x, square root of x plus h. Those two terms are going to cancel. That happens every single time. I had to go over it this time just so you can see it. At this point from here on out, if we're using the conjugate, just multiply the first terms and the last terms. All right. My last terms, negative square root of x times positive square root of x. That's going to give me a negative x, as it's still being divided by h times the square root of x plus h plus the square root of x. Up top, we have x plus h minus x. We actually can drop off that parentheses. These x's are going to cancel. Negative x and positive x cancels out. The h's are actually going to cancel as well. I'm just going to show that step just in case somebody needs to see it though. So we're left with h over h times the square root of x plus h plus the square root of x. Here my h is canceled. Now we're evaluating the limit as h equal to 0 for 1 over the square root of x plus h plus the square root of x. Now, here, this is still a rational function, but we can solve this through direct substitution. We couldn't in the beginning because we would have had 0 on the bottom of our fraction. Here, though, if we replace 0 for h, we don't end up with 0 on the bottom of our fraction. So this ends up being 1 over the square root of x plus 0 plus the square root of x, or 1 over the square root of x plus the square root of x. And we know 1 square root of x plus another square root of x will give me 2 square roots of x. So f prime of x will be 1 over 2 square roots of x. This is a reminder, f of x, square root of x. Any questions on how we got that domain? Oh, excuse me, not domain, but any questions on how we got f prime of x? So now what we want to do is compare those two graphs. Now this particular function doesn't have any horizontal tangents, so we won't have any x-intercepts. But as far as the interval of increase and decrease, it still holds true. All right, so the graph of the original function, f, the square root of x. We know that graph starts at 0 and looks like a lowercase r, defined only on the positive side. F prime of x we found to be 1 over 2 times the square root of x. This graph is also defined only on the positive side. And that's going to be the sketch for the graph of F prime. Now, the characteristics that we're looking for as far as the x-intercepts don't hold true. We don't have any horizontal tangents here. We don't have an increasing or decreasing or vice versa. But we can see that here, all of our horizontal tangents, or excuse me, all of our tangents if introduced are all will be positive. All right. There's no part on this where it will be a negative horizontal tangent if we introduce one. Notice that for this graph, it's only defined above the x-axis. All right. Also has a horizontal asymptote of the x-axis, which means it never has an x-intercept, which makes sense because we don't have any horizontal tangents on the graph of the original. Now to answer our question, the domain for f prime of x, the domain would be from open parentheses 0 to infinity. The difference between this function and its derivative is the domain for the original function to open bracket 0 to infinity, which means that 0 can be evaluated on the graph of x. 0 cannot be evaluated on the graph of this derivative. And this makes sense because if x is 0, then we end up with 1 over 2 times the square root of 0, or 1 over 0, you can't divide by 0. All right, say it again. Here, we can take the square root of 0. The square root of 0 is 0. That's a real number. It's a part of our domain. We can evaluate it. But the graph of this derivative, we can't include 0 because the derivative is a quotient, 1 over 2 times the square root of x. And if we try to evaluate x as 0, we end up with 1 over 2 times the square root of 0, or 1 divided by 0. We cannot do it. This is why we have a vertical asymptote here, but we don't have one here. Now there is an arbitrary horizontal asymptote here, which means in the higher level math course, it means that it's a step function. All that's saying is that that's why we have a horizontal asymptote, because there is no x-intercepts. All right. Any questions on that? I apologize. You gotta take a second, make sure yourself is in silent while I do the same. But any questions on that example though? All right, so notice that those characteristics still hold true, even in this example. All right, example 4, one we're dealing with a quotient. These are usually the ones that kind of mess people up with their algebra, but it's only because of the fraction. All right, so in example 4, we're asked to find f prime if f of x is equal to 1 minus x over 2 plus x. All right, so given our f of x, which is 1 minus x over 2 plus x, we use our formula to find f prime of x. So this is the limit as h approaches 0 for f of x plus h minus f of x all over h. All right, so in this case, we will be evaluating the limit as h approaches 0 for 1 minus x plus h over 2 plus x plus h minus 1 minus x over 2 plus x. And all of this is being divided by h. All right, so now at this point, it's going to typically where I lose people because of the algebra. The text is going to always make the assumption that the algebra is a given. Remember, we went over the flying X technique. Remember, the flying X technique is whenever we're adding and subtracting fractions. Here, we have two fractions, very complex with abstract denominators, but at the end of the day, we have a fraction minus a fraction. So we can use the flying X technique. Top left times bottom right, 1 minus x plus h times 2 plus x. Take the sign in the middle, minus bottom left times top right, 2 plus x plus h times 1 minus x. All being divided by the bottom times the bottom, 2 plus x plus h times 2 plus x. This is all still being divided by h. I'm saying all of this because this expression is going to look like I pulled it out of the F, but we can always refer back to that flying X technique because it's really just because our denominators are so complex. So we're still evaluating the limit as h approaches 0 for 1 minus x minus h times 2 plus x minus 1 minus x times 2 plus x plus h. And this is all being divided by h times 2 plus x plus h times 2 plus x. Now we refer back to the flying X technique, and we're just, for right now, we're just going to ignore this h in the denominator. But we have top left times bottom right, 1 minus x minus h. Once we distribute that -1, that's where we got this from. Times bottom right, 2 plus x. Take the sign in the middle, minus bottom left times top right, 1 minus x times 2 plus x plus h. And it's all over the bottom times the bottom. 2 plus x times 2 plus x plus h. So a logical question is, where did this h come from? All right. So remember, when we have a fraction divided by a fraction, or here, let's just look past the complexity of this problem at the end of the day, this answer is going to be a fraction. Even if it's a whole number, we can turn it into a fraction by putting it over 1. All right, so we have a fraction divided by a whole number. We can easily turn h, that whole number, to a fraction by putting it over 1. Now, we have another algebra technique that they take for granted. Remember, technically, we can't divide a fraction by a fraction, but one technique to where you can divide a fraction by a fraction, for example, 1/3, excuse me, 1/2 divided by 1/3, is to use keep, change, flip. All right, so we're going to keep the top fraction the same, change division to multiplication, and then we're going to flip the bottom fraction. This is still true here. So we have whatever this fraction is, which is this very complex fraction that we have without the h. And we're going to multiply it by changing division to multiplication and flipping the bottom. So what was h over 1 is now flipped to 1 over h. And 1 over h times this complex fraction here, 1 times the top is itself. The bottom, h times 2 plus x plus h times 2 plus x, is just simply h times 2 plus x plus h times 2 plus x. All right, so that's where this complex fraction came from. Any questions so far? All right, so now we need to multiply them to see if we have anything to cancel out. So we need to multiply the trinomial 1 minus x minus h by the binomial 2 plus x, as well as multiply the binomial 1 minus x times the trinomial 2 plus x plus h. And we don't want to forget that there is an understood -1 that's in front of the second quantity, which is going to change every sign from positive to negative and vice versa. So still evaluating the limit as h approaches 0. We're going to have, well, let me make sure, I'm going to bring it down, I'm going to need some space here. So evaluating the limit as h approaches 0 for 2 plus x minus 2x minus 2h minus x squared minus xh. This is the polynomial we get for multiplying 1 minus x minus h times 2 plus x. Minus 2 plus x plus h minus 2x minus x squared minus xh. All of this is still being divided by h times 2 plus x plus h times 2 plus x. Out of curiosity, if anything like I was, getting this polynomial from this multiplication may not be so obvious because there's a lot of different ways you can do it. All right. Me personally, whenever I'm multiplying a trinomial and a binomial, I just think of it as distributed. I'm gonna multiply everything in here by 2, and I'm gonna multiply everything in here by x. 2 times 1 gives me 2. 2 times negative x gives me a negative 2x. 2 times negative h gives me a negative 2h. Then I'm gonna multiply everything by x. X times 1 gives me x. X times negative x gives me a negative x squared. And x times negative h gives me a negative xh. All right. So this is very, very complex because it's so tedious and it's a lot of different terms all at once. It's a lot of opportunities to make a mistake. But don't forget that if you slow down and just use the rules as you know them, you should not have a problem with it. Also keep in mind, I'm only going to ask like 2 problems like this on the test at most. And it wouldn't be one that's this complex. This is a good homework problem for understanding, not a good test problem. We want to remember that we're going to distribute this -1, which is going to change every one of these signs to their opposite. So what was positive becomes negative, what was negative becomes positive. And we'll notice that a lot of these terms are going to cancel out. All right, so when we combine our like terms, we're going to be evaluating the limit as h equal to 0 for -3h divided by h times 2 plus x plus h times 2 plus x. And that's what we get when we combine all of our like terms. All right. Would anybody benefit from me showing how these terms cancel out? Because there's only really 2 terms left over. And that's that -2h and this -1xh, which actually gonna, excuse me, this negative Yeah, this negative x, well, this positive x. I'm sorry. If you see the same thing in both of these parentheses, they're going to cancel out because this -1 changes it. So this 2 and this 2 cancels out because this 2 becomes -2. This x and this x cancels out because this x becomes -x, and so forth. All right, the only thing that we're going to be left with is two terms with h's. We have a -2h, and we have this negative h, or excuse me, this positive h, which becomes negative, and we combine those like terms, we get -3h at top. But these h's cancel. So now we're evaluating the limit as h equals 0 for -3 divided by 2 plus x plus h times 2 plus x. We can solve this through direct substitution, even though it's a rational function. Because now if we replace h with 0, we do not end up with 0 on the bottom of my fraction. So we end up with -3 divided by 2 plus x quantity squared. And this will be equal to f prime of x. All right, just to be clear, in case anybody has a question, this h becomes 0. So we're left. Good. All right. So this h becomes 0. We're left with just 2 plus x plus 0, or just 2 plus x. So we have 2 plus x times 2 plus x. By definition, that's 2 plus x squared. And I think we're out of time. Listen, I'm gonna finish up these examples because we need to finish these examples before our lab. I'm gonna film it today, send you an email so you can review it tomorrow in preparation for our lab on Friday. All right, I wanted us to go through these long ways of doing it because next week when I show you the formulas, you're never gonna take this route again. All right, keep in mind, you do have to do this once or twice on the test. So you do need to know how to do this, but once 2.3 starts, you're gonna realize that it's a much, much quicker way of analyzing these functions. All right. Well,
That's just the f of x plus h minus f of x over h.
as h equals to 0.
And that's what we have to do.
Yeah, when it comes to the limit definition, or the limit definition of a derivative. And you'll see that on the test too. All right, but for tomorrow,